Hi, welcome to this session on axial flow compressor. In the previous session, we understood the velocity triangles and how it is drawn, what are the components of a typical velocity triangle. Now we will try to understand different relationships based on the trigonometric concept. Let's get into it. The first relationship is for rotor entry, where we define the axial velocity in terms of absolute velocity, right? So if I do that, so I can write CA1 as CA1 cos alpha 1, means if I apply the trigonometric relation cos of angle alpha 1 to this particular triangle, I'm going to get cos alpha 1 as CA1 by C1, and I can represent the axial velocity in terms of absolute velocity. Similarly, if I change the angle from alpha 1 to beta 1 and I draw the relationship for this velocity triangle, then I get a relationship between axial velocity and the relative velocity in terms of beta 1, that is the blade angle, right? So I can write CA1 as W1 cos beta 1. I call it as equation number 2. Similarly, I can represent the tangential component of the absolute velocity as CT1, which is equal to C1 sin alpha 1. And similarly, that is equal to C1 tan alpha 1. We call it as equation number 3. Now, it is very important to give numbers to the equation because a lot of equations are there and we will be using these equations in the coming analysis. For example, work and the degree of reaction derivation, we will be using these equations. So please make sure that you give numbers to the equation. Alright, then I can also define the swirl velocity or the component of relative velocity in terms of relative velocity and axial velocity, right? So this is very interesting use of mathematics in physics, right? So you have sine beta and tan beta for again the same triangle, where I can represent the tangential component of relative velocity in terms of relative velocity itself or in terms of axial velocity. Now moving on to the vectorial relationship between the velocity components, I can write the peripheral velocity as the sum of the u is the sum of the tangential component of relative velocity and the tangential component of absolute velocity, right? So I call it as equation number 5, and then if I substitute the value of the tangential component in terms of air angles and beta angle, I can write u as C1 sin alpha 1 and W1 sin beta 1. Let's call this as equation number 6. I have just substituted the value of CT1 and WT1 in this equation number 6. Okay. So similarly, I can substitute the value in terms of tan. So equation 3 and 4, again in equation 5, I get equation 7. So the only difference between equation 6 and equation 7 is that equation 6, we have used the absolute velocity of air C1 and relative velocity W1, right? So if I don't have these values, then I should go for the axial component, because in most of the analysis we assume that the axial component of the compressor stage remains constant. So that is the assumption we make in majority of the cases and even in the conceptual design phase. So if I know the value of CA1, that is the axial component, then I can easily calculate either of the air angle or the blade angle if the peripheral velocity is known. Of course, this will be a given value And if I know the value of the axial component, I can easily find out the air angle or the blade angle from equation number 7. So that is the difference between equation 6 and equation 7. Moving on to the rotor exit. In this case, we will use the same funda, and then we define the axial velocity, tangential component of absolute velocity, and tangential component of relative velocity. And also the peripheral velocity is represented in terms of absolute velocities and the axial velocity. We call it as equation 12 and equation 13. So you can pause the video here, note down all the equations with the equation number for the exit velocity triangle of the rotor. All right. Now we will try to get the values of absolute velocity in terms of axial or relative, right? So one assumption, as I discussed just now, is that the axial velocity through the stage is assumed to be constant. So what happens if I assume the axial velocity as constant, right? So when I say axial velocity is constant, that means CA1 is equal to CA2 and that is equal to CA3. Okay, so all these velocity vectors are equal. Now if I assume that, I can write a general CA which is equal to C1 cos alpha 1 or W1 cos beta 1 or C2 cos alpha 2 or W2 cos beta 2. So this is a very important relation. When we go for numericals, we will use this idea of constant axial velocity, and then the problem becomes very simple to do the analysis, right? Now if I assume this axial velocity as constant throughout the stage and submitting it in equation 7 and equation 13, I get the ratio of U by CA, that is the peripheral velocity of the rotor blade, absolute velocity of the air. I get a relationship between the peripheral velocity of the rotor blade and the absolute velocity as tan alpha 1 and tan beta 1, and that is same as tan alpha 2 and tan beta 2. So let's call this as equation number 15. Now please you can pause here and derive this equation. Very simple, just the substitution. Moving on. Now if I apply this to equation 5 and equation 11, I get CT1 plus WT1 means the tangential component at the rotor entry that is equal to the sum of tangential components at the rotor exit. Means, see here, the U value is same at the inlet and at the exit of the rotor blade, right? So if I call this as the leading edge, so usually in aerodynamics we use for an airfoil the leading edge where the air enters or touches the frontal portion of the airfoil, and if I call this as the trailing edge, so the peripheral velocity of the rotor blade is same at the leading edge and the trailing edge. That means U remains constant. When I say U is constant, that means CT1 plus WT1 is equal to CT2 plus WT2. I hope you're getting the concept. Then I can simplify this equation, bringing the tangential component of absolute velocity on the left hand side and the tangential component of the relative velocity on the right hand side. And then if I substitute, I get the relationship between the air angles and the blade angles. So let's call this as equation number 16. So equation number 16 gives a very important relation between the air angles and the blade angles if the axial velocity is constant, right? So if axial velocity is constant, I have a relation between the air angle and the blade angles, right? So we will end this session now. In the next session, we will talk about the work absorbing capacity of a compressor stage.